C, grade 12 college prep physics. This is our introductory lesson on friction. There's going to be two videos related to friction. One is general friction, the second is specific to solving for the coefficient of friction, which we'll talk about later. But friction is the force that always resists motion. So it's always in the opposite direction of motion, always, no matter what the case is. It could include air resistance, though we don't generally include that in our type of calculations. We focus on friction between surfaces. Just before we get in too much into friction, let's just remember the normal force, because normal force is important and a relevant part of friction. So imagine you got the Joker and 80% of his 87 kilograms is resting on the seat. What's the normal force acting up on him? So I have a little free body diagram where we have the normal up is equal to gravity down, because there's nothing else, no other forces acting on him. The only thing that I did is, so normal equals gravity, 0.8 meaning 80% of the 87, okay, because we're saying that some of his mass is in his, is maybe supported by the floor or whatever, so that only 80% of his mass, and that's where that's coming from, okay. Normally we just mg, and then, so the normal force is 682, okay. Okay, so just going back to friction then, there are three types, and I guess there's a fourth type because I didn't mention air resistance or any type of even air resistance or even water. Like there's all kinds of things that you could count as friction, but really we just look at contact friction, and that would be static, kinetic, and rolling. Rolling friction doesn't get discussed in this class in any meaningful way, okay? Static, however, and kinetic do. Static means non-moving. So it's the friction between surfaces that just barely get started moving, and kinetic is also known as sliding friction. No matter what kind of friction it is, it depends on two things. What the materials are that are in contact. So, the best example might be rubber and ice would have less friction than rubber and concrete, right? That's why you slide on ice, there's less friction. So that's the first thing. And then the second thing is the pressure between the surfaces, or the normal force. So how much pressure there is pushing between them, right? If two things are just lightly in contact, they'll slide easier than if they're really pressed together quite hard, right? And that would be a measure of normal force. And that leads to the equation, which is really the general friction formula. Friction force this is called the coefficient of friction, and this is what tells you about the two materials, and then times the normal force. So this coefficient of friction, I call it the stickiness factor, right? And like I say, it just says how much stick is there between any two surfaces. And I could go, let's talk a bit more. Oh yeah, and that's the symbol for it. And you say that as mu. I'm going to show you some examples of coefficients of friction. Basically, someone has researched, I can find it on the internet, you can find bazillion tables of coefficients of friction. So I'll show you that in a little bit, and tables, because, for sure, any engineer that designs anything, they need to know the friction. And it's not just a part of machinery or equipment. In your body, one of the goals of your joints are all lubricated. Well, they're lubricated because you want to have less friction, right, between your joints. And so, friction's a big deal in any process. It is the fact that makes all of our processes inefficient. We lose efficiency in every process that exists because of friction, right? And that's wear and tear on equipment, everything. Friction's a huge deal, and so engineers need to understand it, and that's of course one of the reasons we learn about it. So here's this coefficient of friction. So a few things about it. It's just some number. It's between 0 and 1. It'll be a decimal, 0.5, 0.7. Now, when I show you the table of them, there are actually some numbers, like I've seen 1.4 for aluminum on aluminum, and I don't get that at all. Actually, I want to make that a bonus. If you will find the coefficient of friction, and I don't mean find on the internet, I mean actually do an experiment to solve for coefficient of friction between aluminum and aluminum. I'll give you a bonus because I'm curious about it. Anyway, that's the thing, is this coefficient of friction, any two surfaces would have a different number, right? So if rubber on ice is 0.15, concrete would be 0.7, a bigger number, closer to 1, more friction, more sticky. It doesn't have any units, and it has that symbol, that sort of, it's almost like a cursive U, but it's well, mu is actually what it's called, and it's a Greek letter. So again, if I come here on the internet, I can look up a bunch of coefficients of friction. I've obviously done this before. So like I say here, I could find tons, right? You could look it up anywhere, but this one I've gone on before, it's an old engineer's handbook. So here's a table, and it's saying, okay, say you had this material and this material, so aluminum on aluminum, and it's saying the sliding friction, the coefficient is 1.4. Normally it's always, like you can look at these, they're typically between 0 and 1. A couple are bigger than that. So when I give you a question and you solve for one, I'll give you a question that the answer is between 0 and 1. You'll say, okay, I know I got the answer right because it's like 0.6 or something, right? So this is just a reference. So obviously if the surfaces are dry, the number is bigger than if it's greased. So if we find, like for example here, cast iron on oak, the dry coefficient of friction is 0.49, and that's sliding again. That means they're moving against each other. Static is if they're not quite moving yet. And sliding, greasy is way lower, and that of course makes sense. Greasy is always going to be a lower number because we know greasy is slippery, right? So anyways, this is just an example of one table that I looked up that has a bunch of different materials, and the whole thing is, what are the two? Oh, like Teflon on steel, we know Teflon isn't very sticky, so it's a really low number. I'm really baffled by how high this one is. It doesn't seem like aluminum on aluminum would have that high of a friction. You know, like even if I think I can find concrete and rubber might be on here. Rubber on asphalt between 0.5 and 0.8, right? Yet aluminum on aluminum is 1.4. Anyway, we'll make that a little goal, a little bonus to see if someone can show me aluminum and aluminum. I've got all the equipment. Anyway, so going back to our note, so that's the coefficient of friction, and we'll talk more about that in the next video. Static friction. So when we say static friction, you saw that in the table I showed you earlier. So static friction is a friction force that must be overcome to just start an object moving from rest. And you probably noticed that before. If you're pushing something kind of heavy, it's like you have to give it a little extra shove just to get it started. That's overcoming static friction. And then once it goes, it's actually a little easier to push once you've got it started. And then you're talking about sliding or kinetic friction. But static friction then is Fs, is the symbol for it, and it just has its own coefficient. And just to go back to here, it means that this is the coefficient of static friction, anything down here. So static friction coefficient between cadmium and cadmium is 0.5. Or a better example, I guess, aluminum mild steel, because it's 0.61. And then it has a coefficient of sliding friction as well, and we'll talk about that later. So that's what the coefficient, that's what static friction is. It's the coefficient related to static friction, again, just times the normal force. So looking at a little example, Charlie, my dog Charlie, his mass is 10K. He's not 10K. He's put on pug weight since then. He's more like 13, but we're going to stick with 10 for the example. He's sniffing a tree, and if we knew the coefficient somehow, some study I've done to determine the coefficient of friction between his butt and the concrete was 0.6. So say you knew that for some reason. Then just how much force would I need to apply? I'm dragging on his leash, say I'm pulling horizontally. How much would I have to apply to just get him started moving? And what's that saying? And what I'm saying there then is I need to know the coefficient of friction. So looking at a system diagram on Charlie, he's got his gravity force down, he's got his normal force up, because I need to know the normal force, right? We don't know the normal force. So to just start him moving, I'll have to just overcome static friction. So that's what I'm going to solve for. Here's the information I'm given in the question, the coefficient, his mass, and I need to know this. Normal force in most of these examples is just going to be equal to gravity, mg. So that's the 10 times 9.8, that's just mg. So the static friction force is just all those things multiplied, which is 59 newtons. Okay. The other kind of friction is kinetic. We call it kinetic friction here at school. You noticed on that table it didn't mention kinetic. Kinetic and sliding friction are the same thing. So That's kinetic friction, and it's like you've got an object in motion already, and it's the resisting force, okay? It's the friction when something's already moving. So its symbol is F with a K. One of the reasons, by the way, we call it kinetic and not sliding is, well, static is S, and how many S's, FS's can we deal with? So it's almost always less than static friction. So, and the reason why, of course, is this constant. Now, there's a few examples, I think, if we look. Well, here, this aluminum on aluminum, which has me so baffled. The static is in that range, and it says the sliding kinetic is 1.4, a bigger number. But other times when you have two, like look at the difference on iron. 1.1 for static, and sliding is 0.15, significant. 1.05 here, 0.29. The sliding friction is almost always less. These two, it's less. This aluminum on aluminum, truly an enigma, or a typo. Anyway, the formula then is just the coefficient times normal force. It's always the same. And so if I did a little example, we've got Charlie, say I've got him going, he's still resisting me, so he's dragging his ass, so to speak. Determine the force of friction I must overcome to drag him down the street then. So this is just Fk. So I know his mu k, in this case, is 0.3. It's less than his static friction coefficient. Excuse me. His mass is 10K. And so, again, it's just Fn is going to be equal to the gravity force. That hasn't changed in the two examples. So 10, his mass, times 9.8. And the mu k in this case is 0.3. So it's 29.4 newtons compared to the static friction example was 59, right? So it is less friction, and that kind of makes sense. You can picture that, you've sort of lived that. Anyways, that's as far as I'm going to go with this video. I have more second video related to friction, so once you've processed this, you can move on to the next one.